Okay, let's unpack this.
Let's do it.
So we've been handed some material that it reads like a high-stakes cheat sheet for a big industry certification.
The Dell Networking Design Exam.
Exactly. It's got all the stats you'd expect, 40 questions, 90 minutes, 59% to pass, and, not a cheap ticket either.
And that context is really key, because when a company like that boils down years of experience into a test, what you're really getting is a list of the most critical, non-negotiable best practices.
Right.
We're not here to prep for the exam, but to pull out those universal truths, the core ideas for designing, documenting, and migrating a modern data center network.
That's our mission, to take this one vendor's guide and find the knowledge that applies to any architect building a high-performance network today. We're looking for those shortcuts to understanding the big principles.
It's the difference between memorizing an answer for a test and actually understanding why that answer is right.
So we have to start where every project should start. The planning, the paperwork. Before anyone even touches a physical rack, what is the single most important job for the design architect?
It all begins in the scoping phase, and the most crucial task by far is comprehensive requirements gathering.
And that's more than just counting ports, I assume?
Oh, way more. It's strategic. The architect has to dig deep into the customer's actual business drivers.
Like what?
What applications are absolutely critical? What do the traffic flows look like? What are the security mandates? I mean, these are the things that dictate the real technical requirements.
I see.
If you miss a key business need at this stage, the whole design is flawed from the start. It doesn't matter how good the hardware is.
That makes perfect sense. So once the architect has those requirements nailed down, they have a high-level design, how do you stop, say, 10 different engineers from deploying it 10 different ways? How do you standardize the build before it goes live?
That is where the pre-deployment configuration template comes in.
The template?
The template. It is the definitive rulebook. It ensures absolute consistency. The sources we have really highlight three things you have to lock down here.
Okay.
First, standardized device naming conventions. Second, the entire IP addressing and VLAN schema. And third, the baseline security policies, your ACLs. This is what turns a good plan into something you can actually execute consistently.
That's the theory. But, anyone who's ever racked gear knows the theory doesn't always survive contact with reality.
Hey, that's true.
An IP address is already taken, a cable route is blocked, stuff happens. So if the template is the plan, what's the final record? The document that captures the messy reality.
That would be the as-built documentation. And it is arguably the most valuable document that comes out of the entire project.
The as-built.
Yep. It has to capture the actual state of the network. We're talking the real IP addresses that were used, the exact VLAN, the physical paths the cables took, every single last-minute change.
So why is the as-built so much more important in the long run than that initial plan?
Because the initial plan is a good guess. It's fiction. The as-built is fact. Operationally, that's everything. Compliance teams need it for audits. When something breaks at 3 a.m., the recovery team needs to know exactly what was connected to what.
Without it, they're flying blind.
Completely. If you don't have an accurate as-built, your support teams are basically reverse engineering the network every time there's a problem. You're just creating technical debt from day one.
That leads us perfectly into navigating change, and I mean high-risk change. Let's talk about a brownfield migration.
The fun stuff.
Right. Ripping out a competitor's live working network and putting in new gear. You can't have downtime. This is where architects really earn their paychecks. What are the two absolute must-do best practices here?
Okay, the first one is all about avoiding ignorance. You must conduct an exhaustive review of the existing configurations.
You can't just copy-paste.
That's the trap. So many people fall into it. They think old switch did X, so new switch can do X. It's dangerous because you need to understand the hidden dependencies, the legacy features, the weird traffic flows that rely on some obscure setting. You just cannot assume that an old config will translate one-to-one to a new platform. It won't.
Okay, so that's practice one.
Yeah.
Know what you're replacing. What's the second one? For the deployment itself. How do you make sure that if something goes sideways, the business doesn't grind to a halt?
You do it with a phased migration plan. One that has safe, pre-planned rollback options built right in.
So you don't do it all at once?
Never. You break the cutover into small, manageable pieces. Yeah. If you try to swap the whole network in one go and hit a bug, you're just left with panic.
Right.
A phased approach lets you bring up the new services alongside the old ones for a bit, you validate everything, and then you decommission the legacy gear. You always have a safety net.
Okay, let's switch gears from strategy to just raw speed. Modern network fabrics, they need massive bandwidth, especially between the spine switches. So if a design calls for 100 gigabit Ethernet, what's the specific hardware that's become the industry standard for that?
The standard you're looking for is the QSFP28 transceiver.
QSFP28.
Yes, and this is a really key architectural choice. The move to 100G isn't just about making things faster. It's about how you get there efficiently.
What do you mean?
The QSFP28 is so popular because it supports 4 independent 25 gig per second lanes. It bundles them into a single high-density, low-power package. It's fundamental to building a really scalable fabric without needing, tons of extra space and power.
That word you used, fabric, brings us right to the heart of modern data center design. This massive shift away from old layer 2 protocols, stuff like spanning tree,
Spanning tree.
and toward pure layer 3 routing. What's the protocol that's the engine for a modern routed fabric?
Yeah.
And what problem does it solve that L2 just couldn't?
The engine is BGP, Border Gateway Protocol.
BGP. But isn't that for the internet?
It was, but now we use it inside the data center. And the main reason, the architectural benefit, is something called ECMP.
Equal cost multipathing. That's the key term, isn't it?
It is the key. ECMP is revolutionary compared to the old L2 world.
Explain that. Why?
Okay, so in an L2 design, a protocol like spanning tree is, well, it's defensive. It actively blocks your redundant links to stop loops, which means half of your expensive bandwidth is just sitting there turned off, doing nothing.
Just in case?
Exactly. BGP with ECMP is the opposite. It's aggressive. It actively uses all available paths at the same time. You get this massive predictable bandwidth and you completely get rid of those blocked links. The whole fabric is lit up.
So you're going from a defensive strategy to a performance-driven one.
That's a perfect way to put it.
Okay, that makes sense for normal traffic. But what about storage? ISCSI traffic, for instance, has like zero tolerance for dropped packets.
Right.
Traditional Ethernet is lossy. It just drops packets and assumes they'll be resented.
Yeah.
So when you're designing for ISCSI over something called data center bridging or DCB, what are the two critical things you need to do to make that link lossless?
Right. So you're dealing with a couple layers of complexity here. The first absolute requirement is configuring PFC, priority flow control. It's a mechanism that basically tells the sending device to pause for a specific type of traffic, in this case, ISCSI. So the switch never has to drop a storage packet because it's congested.
So you have to identify the ISCSI traffic and then apply this PFC to it.
You absolutely have to. That's how you get lossless behavior.
And what's the second requirement? It sounds like it goes back to that as-built idea of making sure things actually work together.
Precisely. The second requirement is verifying end-to-end compatibility. The architect has to check that the storage array itself is fully compatible with the network OS's specific DCB features.
Ah, so it's not enough for the switch to be doing it.
Not at all. If the switch is sending PFC signals but the array doesn't understand them, or there's a version mismatch, performance can be terrible or even catastrophic. Designs fail because of incompatible parts just as often as they fail because of bad logic.
So an L3 leaf spine fabric is better, but it sounds like it could be incredibly complex to configure by hand.
Oh, it's very verbose.
Which is why automation is so important. If you're deploying hundreds of these devices, how do architects speed things up but also maintain that consistency we talked about earlier?
You need tools that automate entire sections of the build. A great example is something called Smart Fabric Services, or SFS.
And what does SFS do?
Its primary job is to automate the deployment and the lifecycle management of the whole top-of-rack switch fabric. This is especially vital when you're dealing with hyper-converged solutions, things like vSRAIL.
Hold on, why is it so critical for hyper-converged specifically?
Because on a platform like VxRail, you've got compute, storage, and networking all in one box. That network layer has to be ready to go instantly and perfectly to support that integration.
Yeah.
SFS handles all the underlying L3 BGP stuff automatically. The customer can just focus on their VMs, not on wiring up the backbone.
That handles the big picture automation. But what about those small, annoying manual errors? A typo in a VLAN ID, a missing ACL entry.
For that, you need something more like a script generator, a tool like FastScript.
Ah.
Yeah. It takes the high-level design as input, and then it generates pre-validated, standardized configuration scripts. It's basically a quality control layer.
So it prevents typos.
It prevents typos that can take down a network. If your design says VLAN 100 is for production, FastScript Make sure that config is applied identically and correctly
Okay.
across all 50 of your switches. In a complex BGP fabric, a single typo can break everything.
So let's look at the future of the network OS itself. We're seeing the rise of enterprise SONiC software for open networking in the cloud. It's open source, it's modular. Who is this for? What kind of environment is this disaggregated approach best for?
SONiC is really designed and optimized for a very specific environment, a large-scale cloud-native data center.
Cloud native.
Exactly. An environment that thrives on separating the hardware from the software. It's for organizations that need APIs to constantly manage the network, that demand flexibility and performance, and don't want to be locked into one proprietary vendor. It's moving the intelligence from the hardware to the software layer. Hashtag outro. So when you put it all together, what does this all mean for someone designing a network today?
What's the takeaway?
Well, this deep dive really confirms the data center is undergoing a fundamental shift. The core principle is moving away from that brittle, complex Layer 2 world with all its blocked links and manual work and embracing the scale and predictability of standardized Layer 3 fabrics.
Driven by BGP.
Driven by BGP. That architecture, backed by rigorous documentation and powerful automation tools, that is a universal blueprint for a resilient network.
So we started with a specific exam guide, and we ended with the modern standard for building high-speed infrastructure.
That's right.
Now, here's a final thought for you to explore. We've talked a lot about how BGP and ECMP are used to maximize bandwidth and ensure things are predictable, solving that old L2 problem where you needed complexity like spanning tree just to keep from breaking. So if the modern goal is to eliminate waste and unpredictability, what's the measurable long-term technical debt? The cost in troubleshooting hours and stability problems and wasted hardware that your organization is carrying right now by not fully moving to a standardized routed L3 fabric.
Think about the operational difference between troubleshooting a known route and debugging a complex L2 convergence issue.
That's a question worth calculating in your next design review.
Well,
We'll see you on the next deep dive.